Hey everyone, I wanted to go over another problem with you guys. This one goes over the Unit 7 problems, so your total response. Um, the reason I wanted to go over this specific problem is because this one deals with a capacitor, and I had some requests to go through an inductor, an RL, and then also an RC problem. So we're going to do that. This one's pretty simple, as you'll see. So I think it's a good conceptual question. And this one is 7.22. So, yeah, as we go along in this video, I'm going to assume that you guys have looked at the previous video, so I don't need to go into the theory as much. And you've also looked at the Discord notes I've sent as well. So hopefully those things can help you guys. And so, yeah, we're not going to go so much into the theory. We're just going to kind of go through the problem together. So hopefully this is helpful to you guys. So let's get into it. So this is our schematic here. As you can see, we just have a current source, some resistors, and a capacitor. And problem A, we're asked for the initial voltage, this nodal voltage, so the voltage across the capacitor, in other words, the time constant, the voltage as a function of time across the resistor or across the capacitor, the initial energy stored inside of the capacitor, and then we're asked for the how much time it takes to dissipate 75% of that initial energy stored in the capacitor once we close this, or once we open the switch, which we can see here. We can see that the switch starts closed and it's going to open. So yeah, and then also I have written down the generic total response equation for voltage. So yeah, let's get into it. Okay, so to start things, we're initially in part A, we're asked for the initial voltage across the capacitor, or the nodal voltage across, that capacitor and that resistor. So I'm just going to redraw the circuit, and this is the initial, so before we open the switch. So first things first, when we look at a capacitor before we open that switch, it's going to act as a open. So we're just going to redraw the circuit like that. So we're going to have our amp source, our parallel resistor, like this, our resistor here, and then we have that capacitor, but remember that's an open, and then we have this resistor in parallel with that capacitor. So we have this open here, so I'm just going to actually get rid of that completely and just put this resistor like that, because we do have that open, but why show it when we know that it's an open and no current's going to flow. Okay, so we have 80 kiloohms here, 20 kiloohms here, and 50 kiloohms here, 7.5 milliamps, and we're looking for the voltage across here, because we're looking for the voltage across that capacitor and that resistor, which is this node here. So the voltage across this. Okay, so you can do a couple ways to solve this problem. There's a lot of things you can do here. The thing that stands out to me, and I think the easiest approach to this problem, is recognizing that we can actually do a source transform. I mean, who would have thought, right? We can actually use source transforms to help us with this problem. So if you recognize that this is a Norton equivalent circuit, we can actually transform that to a Thevenin, and then we'll get all these resistors in series, and then it becomes a simple voltage divider to get the nodal voltage across this resistor. So that's how I would do it. So let's just do it that way. You could use mesh or nodal analysis if you wanted to, or another method, but I think this is the easiest. So we're gonna do our source transform. So to do the source transform, we just gotta find the voltage for our voltage source. So we gotta find V equals IR, so we need this amp source here, and then our resistor that we're gonna move. So the voltage is gonna be 7.5 times 10 to the negative 3, because it's milliamps, times 80 to the third power, or times 10 to the third power, because it's kiloohms. So that's gonna give us, that will give us, so 7.5 times 80, 600 volts. Okay. And then I'm going to redraw our circuit as a voltage source. Now we got that 80 kilo ohm resistor, our 20 kilo ohm, and then our 50, right? Okay, and this is 600 volts, and so we want, you know, this node here. That's what we want. In other words, the voltage across this resistor. So we could add these in series pretty easily, and then you can see that we would have a voltage divider, right? So I'm just going to, in my head, add them together. They're gonna become one resistor. So our voltage divider formula, so if we want the initial voltage across this node here, it's gonna be our first resistor, our second resistor, so 50K, over our first plus our second. So these two are going to be our first resistor. You know, that's going to make that up because, like I said, we can just add these in series to get that voltage divider. So it's just going to be 100K plus 50K, like that, and then times our initial voltage source, which is going to be 600 volts. So if we add 50 over 100 plus 50 is just going to be 50 over 150K. So that's just gonna be 1/3, so 1/3 times 600. So we're gonna get 200 volts as our initial voltage right here. So there we go, we got it. That's part A done. So I think that's a pretty easy way to do it. So let's do part B now. I'm gonna erase some stuff. Okay. Let's see. Okay. And I'll just leave that up here. So we'll say 200 volts like that. And then part B, we're looking for tau, which we know is just gonna be our equivalent resistance times our capacitor. So now we're looking at when we have the, after we open that switch, right? Because now we're looking at when time hits 0 or after 0 from that point on. And I'll put that here, so when time is greater than or equal to 0. So when we open that switch, I'm just gonna draw a circuit. You know, we're gonna have that open at the switch. So we're really just gonna have a pretty easy circuit to deal with. So we got our 0.4 microfarads. Oh, that's gonna poorly drawn. Okay, and then we got our 50K resistor like that. Okay. So, I mean, our equivalent resistance is just one resistor, right? So 50K, and then we have our 0.4 microfarad capacitor. So we're just gonna say tau is gonna be 0.4 times 10 to the negative 6 times 50 to the third power, which is all gonna be equal to, let's see, 0.4 negative 6 times 53. Okay, 0.02 seconds, or in other words, 20 milliseconds, okay? So I'm gonna put that here, 20 milliseconds, like that, okay? And that's part B done, so pretty easy, right? I'm gonna leave this circuit up here. And so part C now asks for the voltage, that we found that initial voltage as a function of time. So if you recall our general form for the total response, V of t is going to be equal to our long time voltages. That's what that infinite sign means. Like, so when t is very, very great. So when our time, after a long time, in other words. And then it's going to be, is that a plus? Yeah, so then plus our initial voltage minus our long time, all of that's going to be multiplied by e to the, or is it t tau? Yeah, t tau, sorry. T tau. Or in other words, I'm just going to rewrite that as RC because we in this specific problem, it's a capacitor, so RC. So if we look at this circuit here, we don't have any independent sources, right? It's just the capacitor and the resistor. So in this case, our long time voltage, or in other words, our steady state, is just 0 volts, right? So if, because there's no independent sources. So in other words, we're just looking at the transient here, because this describes our total response. The total response is made up of the transient and the steady state. Our steady state is just 0, so we're just looking at the transient. So I'm just gonna plug those numbers in, and actually I'll just plug the entire thing. So, our long time is just 0 volts, and then our initial is 200, right? So we'll just plug those in. So our initial is 200 minus 0, and then e to the negative t RC, which we found to be 20 milliseconds. So 1 over 20 milliseconds, because I just want to do this, is just 50. So e to the negative 50 t, like that. So in other words, our voltage is going to fluctuate as so when, well, technically when t is greater than or equal to 0, but yeah, so like this. Okay, so and if you wanted to conceptualize what that looks like, you could just go into Desmos and see. But yeah, we're basically going to see that our voltage over time is it's an exponential decay. So that's part C. So I'm just going to draw that up here. 200. So 200 e to the negative 50 t. Okay, when time is greater than or equal to 0. So there we go. That's part C. Oops. Okay, so what we got there? Okay, so on to part D. Part D is asking us for the initial energy stored in the capacitor. Okay, so that's what we're looking for. If you recall, our initial energy is equal to 1/2 times our capacitance times our voltage. So, and with the initial, it's just going to be our initial energy storage is going to be our capacitance, because it doesn't change, and then times our initial voltage squared, right? So I have that here. So now we just plug our values in. It's as simple as that. So 1/2, and then our capacitance is 0.4 times 10 to the negative 6 times our initial was 200 volts, right? So 200 squared. Okay, and let's just plug that into the calculator. This times 0.4, negative 6 times 0.5. Okay, so it's equal to 0.008 joules, or in other words, 8 millijoules, like that. Okay, so pretty easy. 8 millijoules. Okay. So moving on to the last part. So this is probably the most in-depth question. It's asking for how long does it take to dissipate 75% of that energy? So what we need to do is we need to find our energy stored in the capacitor as a function of time, right? Because we need to solve for that time. We already know the formula for the energy stored in the capacitor. So it's the same thing. Now we're just making it more generic by just saying it's a function of time. So we need to plug in our voltage as a function of time. So if we do that, it's going to be 1/2 times our 0.4 times 10 to the negative 6 times 200 e 50 t squared, like that. Okay, and then our initial energy stored in our our energy stored as a function of time in our capacitor. We already did this initial thing, so we just know it's 8. So I'm just going to say 0.008, and then it's going to be e to the, when we have two exponents, we multiply them, so negative 100t, like that. And of course, this is all when time is greater than or equal to 0. So now, from here, we know that we're looking at when 75% of the energy is dissipated, right? So if I have 8 millijoules, we just say, what's 75% of that? Because that's what we're looking for. So 75% of 8 is 3/4, which is just 2. So when we're looking at how long does it take for our capacitor to go to 2 millijoules, right? So I'm just going to, I'll write that up here. So 75% is going to be 8 millijoules times 75, which is just going to be 2 millijoules like that, okay? And I'm just going to plug that in. So 0.002 in other words, and 0.008 e to the negative 100t. And now we're just left with t, so we just got to solve for t, right? So we're just going to do some algebra. So 0.02 or 0.002 and 0.008 is just going to simplify to 1 for e to the negative 100t like that, right? Just doing some simplification. I'm going to bring the 4 over, so 1/4 equals e to the negative 100t, okay? So we have e raised to a negative exponent, so in other words, it's just an inverse. So I'm gonna write that out as 1/4 equals 1 over e to the 100t, like that, okay? And now I'm just gonna take the inverses of these inverses. So that's just gonna look like we're gonna get 4 equal to e to the 100t, like that, right? Okay. And now we have Euler's number, so the reverse operation is going to be the natural log. So natural log of 4 is going to give us 100t. So t is going to be 1/100 times natural log of 4. Okay, I think my math is right. Let's see. So 1/100 natural log. Natural log of 4 times this. Okay, so I get that t is equal to 139, sorry. Or in other words, t is going to be equal to 13.9 milliseconds. Okay, let me double check if that's right. Yeah, okay, cool. So now we have part E. So when we dissipate 75% of our initial energy stored in the capacitor, that takes roughly 14 milliseconds. Okay? Okay. So yeah, that's literally it to this problem. So a pretty simple problem. And yeah, hopefully this made sense conceptually and going through it. I hope this helps you guys. But yeah, that's really all there is to it. So yeah, if you have any questions or anything like that, again, just let us know. And yeah, have a good one.